Greetings, ladies and gentlemen. Today we're going to look at 3.1 maximum and minimum values. When we are working with different types of functions, we know that when we look at the graph of the function, they have ups and downs or curvy behavior, right? Let's say if we have graph something like that, right? Okay, and we can see that they have different points where, let's say here we have a little top of the hill and the bottom of the valley, and then another top of the hill right here and the bottom of the valley right here, right? So these are some sort of maximum and minimum values among their neighborhood, right? Let's say if we're just looking at this interval, then the point A will have the highest value, and that's going to be what's called a local maximum. And we will look at those in a little more details in this section. All right, so let's start by analyzing this picture that we have right here. So we can see that at this point, which has the coordinate 3, 5, that is the largest value, right, on this pink line, right, the largest value. And we also see that another point, which is down here, which has the coordinate 6 and 2, and that is the smallest value. Right? And what we're interested in is, given some function f of x, how do we find these type of points, right, where you have the largest value or the smallest value? And that's what we're interested to see. And furthermore, right, this is when this basically says f of 3 is equal to 5, and here we know that f of 6 is equal to 2. Now notice that the only x values that we're looking at on this graph is between x equal to 1 and x equal to 7. And for this pink line, this function between x equal to 1 and 7, we saw that when x is equal to 3, we have the largest value, right? And when x is equal to 6, we have the smallest value. So we can say that this f of 3 is equal to 5, which has the largest value. We can call that the global maximum, because it has the largest value, it has the maximum value on this graph. And similarly, we can call f of 6 equal to 2. The value of 2 holds the name global minimum. And again, because it's the smallest value on this graph. Now, notice that when we talk about the graph on this example, we are only taking x value between 1 and 7, because you can see that to the left of 1 and to the right of 7, there is nothing that tells us about how the graph is going to behave, right? So we are looking at just a segment of the graph in this example, and we can say that, yes, this point right here, let's call that point A, is the global maximum, and point B is the global minimum. And let's take a look at the definition. This is our first definition. Let C be a number in the domain D of a function f, then f of C, which is the function value, is the absolute maximum value of f on D if f of C is greater than or equal to f of x for all x in D, or absolute minimum value of f on D if f of C is less than or equal to f of x for all x in D. Now, this definition can be a little bit confusing in the beginning, so let's break it down into different parts and talk about them. First of all, absolute maximum or minimum, right? They are the same thing as global maximum or minimum. Okay. Now, next, let's understand what this part is saying. Right? The value on f on D, right? F on D. So D, keep in mind that D is the domain, right? So on the domain of f, if you can find a value f of c such that it's greater than everything else in the domain, then we call that the absolute maximum, just like our previous example right here. The domain that we see here is between 1 and 7. right? Between 1 and 7. And we can see that this point A that holds the name of global maximum, this value has the highest value because f of 3 is equal to 5 is greater than everything else on the domain, right? So I can write that f of 3 is greater than or equal to any other f of x where x is in 1 and 7, okay? And that is what defines global or absolute maximum. If you can find a value that has the largest function value inside the domain, then we can call that the absolute maximum. And similarly, if we look at the point B, which holds the coordinate 6, 2, or f of 6 is equal to 2, now we can say that f of 6 is less than or equal to any other f of x where x is in the domain 1 and 7. Right? In other words, to say that is the lowest point of the graph, right, in the domain. And for point A, that is the highest point of the graph in the domain. Now, of course, in here again, our domain is between 1 and 7. Okay. And absolute value, absolute maximum or minimum is sometimes called global, right? We can interchange the word absolute and global for in terms of maximum and minimum. And furthermore, the maximum and minimum values of f are also called the extreme values, right? So extreme values of f includes maximum and minimum, right? And to be a little more specific, we actually include global or local minimum. Okay, now we haven't talked about local maximum and minimum yet, but we will do that in a second. But just remember that when we talk about extreme values, we want to know about maximum and minimum, both global and local. All right, next, let's look at the second definition, which has something to do with local maximum and minimum. Now, before we dive into the definition, another way that we can say about local maximum or minimum is local extremes. Okay, so we know that when we talk about extreme values, we meant maximum or minimum from earlier. Right? So if we add the word local before extremes, then that means we are only looking at local maximum and local minimum. And let's take a look at what that means. Right, so far up to this point, they are pretty much the same as a global maximum and minimum, right? You want to find a max value such that f of c is greater than or equal to or less than or equal to f of x. But the main difference here is that the x value, we are only looking at the x value near the point C, near the point C. Okay, so one question that you might think of is, okay, if it's near C, then how close do we want it to be, right? And there is no true answer. There is no specific answer saying, okay, you have to be this close in order to be a local maximum. But let me give you a graph to show you what we're looking at. Hey, let's say we have this function right here. And let's start by looking for global maximum, right? Let's start with global extremes. Meaning you want to look for the highest point and the lowest point of the graph, right? So the lowest point is probably right here, it's A. Right? So we have global min at A. Okay, and let's look at the highest point of the graph. It's right here. Right, that's D. And we can say that, okay, global max is D. All right, so global is pretty easy to find, right? I should say f of A and f of D. A and D are the x value, and f of A and f of D represents the function value. So when we talk about minimum or maximum, doesn't matter if it's global or local, we have to talk about the function value instead of the x value. Okay, now let's talk a little bit about what local extremes are. Okay, so local extremes, you can think about it as it's the highest point in its neighborhood. Okay, it's the highest point or the lowest point in its neighborhood. So let's do this. Right? For example, we see a bump right here, right at B, right? A bump right here. So it feels like the top of the mountain. Right? So this is what we call a local maximum, right? Because it's the highest point around this area. And one easy way to do that is you can just draw a circle like what we're doing here, and then find the highest point. And in this case, B is the where the highest point happens. So we can say that we actually have a local maximum at f of B. Okay, and let's try a local minimum. Right, so you want to find somewhere you hit the bottom of the valley. Right, so another way would be here. Right, we hit the bottom of the valley here, even though there's a cusp or a sharp turn here. But that's okay. That still counts as a local minimum, right? Because it's when you draw a circle like that, it's the lowest point on the graph, right? Around its neighborhood. So we can say that, yeah, so there's a local minimum happening at f of C. So here we have one more local maximum and one more local minimum. Go ahead and pause the video, see if you can find out what the other local maximum and the other local minimum is. All right, so let's take a look. We'll see another top of the hill right here at where x is equal to d. And this is also where our global maximum happens to be, right? F of d. So it's okay that we can have a value, in this case f of d, to be both the local max and local min. And in fact, a lot of the times we will see this where a local maximum happens to be a global maximum as well, and the local minimum happens to be a global minimum, but that's not always the case, and we will dive into more details later. And another local minimum that we have is right here, right, bottom of the hill, the bottom of the valley, right here, f of e, and that's another local minimum. And as you can see that I draw little circles around the top of the hill or the bottom of the valley to know that we have discovered we have discovered a local extreme around that area. And here is another illustration. Right, we have a local minimum happening right here, and you can see that the picture gave us some sort of neighborhood I, which is between 3 and 5. And that's something that you can do, right, if you want to try to find a local minimum or maximum, is, give a fixed interval and see if you can find the lowest value, right? And same thing here, right? We have a local max. And in K, we have a local min as well as the absolute min, right? So in this case, this would be f of 12, which is equal to 3, happens to be both local max and local min. Right, and here is another example that is a little more interesting. We're taking a look at the function cosine x. Now we know for sine and cosine, they are a periodic function, meaning they're going to repeat themselves over and over again until infinity. So we can see that for sine, we do see many local maximum and local minimum. And if you remember correctly, for sine and cosine, they are bounded by 1 and -1, meaning the smallest value a cosine function can output is -1, and the greatest value that a cosine function can output is 1, right? In that case, whenever the function outputs 1, that's where the local and absolute maximum is going to happen, because that's the maximum value cosine can give. And also, whenever we hit -1, that's going to be a local minimum, and as well as the absolute minimum. Right. So if we pay attention to where the values happen, right? Let's say local maximum first, it happens at 0, 2 pi, and it's going to happen again at 4 pi, right? Or -2 pi, right? So we can see that for for local and absolute or absolute maximum, it happens at x equal to 2n pi, okay, where n is any integer. Okay, so whenever the x value is a multiple of 2 pi, then that's where the local max and local min, local max and absolute max is going to happen. So another way, let's look at the local min now, right? The minimum. Right? So the minimum happens at pi, 3 pi, 5 pi, 7 pi, or -pi, -3 pi, -5 pi. All right, so local min and absolute min are going to happen at these values, right? Pi, 3 pi, 5 pi, or -pi, right? -3 pi. Okay, so we can conclude that local or absolute and also absolute min for the cosine function are going to happen at x equal to 2n plus 1 pi, where n is any integer. Right? And I'll talk about what the 2n plus 1 is saying. So 2n plus 1, when n is equal to 0, we get pi. When n is 1, we get 3 pi. Right? And then as you move on, you get 5 pi, 7 pi, and so on. Now you can also make n equal to -1, right? So I will get -pi, -3 pi, -5 pi, and so on. So another way to say that is that for a cosine function, local and absolute minimum happens at odd multiples of pi, right? Odd multiples. Okay, and that's one way for these type of function, which is periodic. We are able to write out where the local and absolute maximum and minimum happens with a general rule, right? So in this case, if it's even multiple of x, we get even multiple of 2 pi. Sorry, even multiple of pi, we get local and absolute max. If it's odd multiples of pi, then we get local and absolute min. All right, now we have our third, not definition, but theorem. It's called the extreme value theorem. Now, before talking about this theorem, what this theorem is going to give us is that what are the conditions so that we can guarantee to have extreme values, right? Local extreme, absolute extreme, and absolute maximum and absolute minimum. All right, so let's take a look at the theorem. If f is continuous on a closed interval, right? So the key here is continuous and closed interval, right? AB. Then f attains an absolute maximum value of f of c and the absolute minimum value of f of d at some numbers c and d in the interval a and b. All right, so what this is saying is if you have a function that is continuous on a closed interval AB, then for sure you are going to have an absolute maximum and absolute minimum. Right, so let's look at an example. First graph, right? So this pink line is continuous, right? And it's on the closed interval AB. So by looking for the highest point and the lowest point of the graph, we are able to say that that is going to be the absolute maximum and minimum, right? So in this case, we have here f of c is the absolute max, and right here, f of d is the absolute min. Okay, and then we have other example as well, right? So go ahead and see if you can identify where the absolute max and absolute min is. Right. So if you want, go ahead and pause the video. All right. So let's see. Here, label it, right? That's, well, it looks like the top of the hill, right? And that is actually the highest point on the interval A and B, right? So here, f of c is our absolute max, right? And right here, f of d is our absolute min. As well as in the third graph, you will see that we actually have 2 points that shares the highest values, right? So in this case, we can say that f of c of 1 is equal to f of c of 2, which are both absolute max. Okay? If you have the same max value, then we can say that these 2 points share the absolute max. And then we also have the absolute min, which is right here, f of d, absolute min. Okay. All right, and here is a non-example of functions that, so in this case, it's not continuous, right? But it's on a closed interval. So we can see that, okay, we do see a absolute min here, right? Which is the lowest point, but can you find a highest point of the graph? Now, maybe you will say, okay, it's this point right here, but notice that it's an open circle. That means the value does not exist, right? So in this case, we don't have any absolute max. Okay? So this is an example where we do have an absolute min, but not an absolute max. Okay? And here is another one. Okay. So we do see that, okay, the lowest point is probably here, but the same idea is that, notice that it's an open dot, right? So there's no absolute min, right? Because we would probably guess that this is where the lowest point is going to be on the graph. But in this case, it doesn't exist, right? So we don't have a lowest point or absolute min. Now on the right-hand side, you can see that this graph shoots up to infinity as the x value gets closer and closer to 2, right? That looks like a vertical asymptote in terms of the rational function, right? But it's going to shoot up to infinity and never stop, right? It's never going to hit x equal to 2. So in this case, we say that there is no absolute max either, right? Because it's non-stopping, right? It's just going to keep going and keep going to positive infinity forever. All right, so here we have a picture giving us an idea on how to find local max and local min. Right, so we can see that whenever we have a local maximum or local minimum, the tangent line is always flat, right? That's the tangent line. They are always flat, meaning they have slopes of 0, meaning that slope is equal to 0. Okay, and we know that when we take the first derivative, it tells us about the slope of the tangent line, right? And that is how we're going to find local maximum and minimum. And here we have our fourth theorem, Fermat's theorem. This is very important, right? Maybe you want to draw stars next to it or a smiley face next to it. If f has a local maximum or minimum at c, and if f prime of c exists, then f prime of c is equal to 0. Okay, it's saying that if we have local max or min, and we can find the derivative, then that derivative will definitely have to be 0 because the tangent line at a local max or min is a flat line, is a horizontal constant line. That means the slope of the line is 0, hence the derivative at those points will be 0 as well. Okay, so we know that if we can find a maximum or minimum, then the derivative will be 0. What about the converse? Is the converse statement true? The converse statement for this would be if f prime of c is equal to 0, then f of c is a local max or min, right? So is this statement true? And let me give you an example, right? Let's look at y equal to x cubed. Now, y equal to x cubed has the domain from negative infinity to positive infinity, which is not a closed interval, right? And you can see from the graph, there is no absolute max or absolute min. What about local maximum? Do we see any local maximum or minimum? Let's see. F of x is equal to x cubed. Right? Now, if we take the derivative by applying the power rule, bring down the power, decrease the power by 1, we get 3x squared. Now, by setting 3x squared equal to 0, we are able to solve for x, meaning x is equal to 0. Now, if this statement were true, right here, if this statement were true, then that means I should have a local max or local min at 0. But if you look at the graph, at x equal to 0, we get this point right here, which is neither, right? It's not a local max nor a local min, right? So this statement is actually false, right? The converse is not true. If we have f prime is equal to 0, it's possible they can be a local max or a local min, but it does not mean necessarily that they are at least one of them. So you might think, then what good does Fermat's theorem do, right? If we cannot find the exact point where local maximum and minimum happen, then what good does it do? But what Fermat's theorem is nice for is that it tells us when or how can we start looking for local maximum and minimum. And here is how. We are going to define a critical number. Now, this definition is also important. A critical number of a function f is a number c in the domain of f such that either f prime of c is equal to 0 or f prime does not exist. So this is how we are going to start looking for local maximum and minimum, is by finding the critical number c by taking the derivative of the function and set it equal to 0 or whenever f prime does not exist. And this means if we combine Fermat's theorem and the definition here, definition 5, we can say the following. If f has a local max or min at c, then c is a critical number of f. Now, sometimes instead of using critical number, some textbooks use the term critical point to explain this number. So they are the same thing. Critical number and critical points are the same thing. All right, so let's do a quick example. Find the critical numbers of the function f of x, 3x squared minus 4x plus 1. All right, so to start, we're going to figure out what f prime is. Right, so f prime of x, which is the derivative of this polynomial, it's going to be 6x minus 4. Now, to find critical points or critical numbers, we're going to set f prime of x equal to 0. That means we have 6x minus 4 is equal to 0, and I'll keep on solving. 6x is equal to 4, and x is 4 over 6, and simplify, we get x is 2/3, right? So x equal to 2/3 is a critical number. Now, that does not mean x equal to 2/3 is where a local maximum or local minimum happens. It's just say that it's a possibility that we have a local max or min at x equal to 2/3. Now, in order to figure out whether it is a maximum, minimum or not, we will talk about that in 3.3. Right, so for now, let's just practice on looking for critical numbers. So what we can do now is we can actually find out where we have absolute maximum or minimum values over a closed interval AB. Right? So we're going to follow these 3 steps. Find the values of f at the critical points, critical numbers of f and AB. Right? So find the critical numbers in the interval AB, and find the values of f at the endpoints of the interval, right? At the endpoints, right? And then we just compare all their function value from 1 and 2, and whichever is the largest one, it will be the absolute max, and whichever is the smallest one, it will be the absolute min. And let's use our previous example to check if we have any absolute max or min. Okay, find the absolute max and min for f of x over the interval -4, 7. Right, so we have a closed interval that is -4 and 7 closed. Right? And we also know from earlier that our critical number, right, f prime of x, which is 6x minus 4, we have the critical number at x equal to 2/3. Okay. So what we're going to do is we are going to compare function values at critical number x equal to 2/3 and the endpoint. So the endpoint of the closed interval is x equal to -4 and 7. So let's do that. We're going to build a table right here, x and f of x. And the 3 values that we're looking at is 2/3, -4, and 7. Okay, so go ahead. We're going to go ahead and plug in all these x value into the function f. And this is what we will have. All right, so we get that the function value when x is 2/3 is -1/3. When x is -4, the function is 65. And when x is 7, the function value is 120. Right? So once you have this table where you're comparing the critical numbers and as well as the endpoints, the lowest value out of all 3, in this case, we have 3 values. Out of all 3 will be the absolute minimum. In this case, we have -3. That's the absolute minimum, right? And the largest value, which is 120, in this case, that will be the absolute max. Okay, so we're going to compare critical points with the endpoints when we have a closed interval for a function. All right, and that's it for 3.1. And thank you guys very much, and see you soon.